Okay, so this is the setup now for number 4. If you've come to this point, hopefully you've given it an attempt on your own end and you've tried to solve and maybe you got stuck, so you're coming here to see where you got stuck. Okay, so here we're looking at the dissolving of solid silver carbonate. So silver, again, is Ag, carbonate is CO3. Carbonate's got a -2 charge, Ag is +1. So your formula is Ag2CO3, and it is a solid. Okay, it dissolves in water, so you would get silver plus carbonate. Silver's +1, carbonate's -2. You're going to need a 2 there. Both of these are going to represent aqueous solutions. Okay, so we have that. Our Ksp, our solubility product constant, is just going to incorporate the products because the reactant is a solid and we don't factor that in because the equilibrium concentration, its concentration isn't changing. Okay, so we square that because of our coefficient 2. And then our carbonate's -2. So this is our Ksp, our setup. Okay, now I'm going to do an ice table just so I can see, what the values at equilibrium are going to represent for our silver and our carbonate. And you can probably guess what they're going to be just if you've done a couple of these problems, but I'm just going to show you an ice table regardless. So we have Ag2CO3. This is a solid. It gives you 2Ag plus CO3. All right, so the solid is essentially not counted since it doesn't factor into your equilibrium constants. And we start initially with no product. Okay, so our change is going to be 2x positive, and then this is just x. So our equilibrium values are 2x and x. Okay, you could probably figure that out by now just by looking at it, but giving you these values, just showing you the full process. All right, now if we look what we're solving for, again, like mentioned in number 3, you're either solving for Ksp or you're solving for a molar concentration of your product. Here they give us Ksp, right? Ksp is provided. And they want us to calculate the molar equilibrium concentrations of your silver ions and your carbonate ions. So I'm going to take the equation that's listed here, move it down. And what we're going to do is we're going to plug in what we have. So for silver, I'm plugging in 2x. So it's really 2x squared. For carbonate, I'm plugging in x. Okay, and then the Ksp value is given right here. It's 8.12 times 10 to the negative 12. All right, so now we want to just use some algebra here. So 2x squared, I'll draw an arrow, so 8.12 times 10 to the negative 12. 2x squared is 4x squared. And then that times x equals 4x cubed. Okay, so then I'm going to want to get my x by itself. I divide by 4. So I don't have this one. So we got 8.12 divided by 4 is 2.03 times 10 to the 12th negative. And I'm just going to move this down so I have room. Equals x to the 3rd power. So I'm cube rooting both sides. So x is going to equal 1.2 times 10 to the negative fourth. All right, so we know what x equals. Now, if we look back at our ice table that we have up here, so here's our ice table, what concentration was x? It was CO3, right? So really, in reality, what this value is showing us is the molar concentration of CO3. Okay, and what value was silver, your silver ions? It was 2x. So for Ag plus 1, sorry, that's minus 2. You're going to take this value and you're going to times it by 2. So 1.2 times 10 to the negative fourth becomes 2.4 times 10 to the negative fourth. All right, so that essentially equals 2x. So these now become your molar concentrations at equilibrium for your products, your silver ions and your carbonate ions. All right, sorry, we went into number 5 here. Okay, I hope that helps. We'll talk more about this on Monday or Tuesday, depending on, Tuesday or Wednesday. All right.